Start.
Hi everyone. Today I'm going to deal the topic of probability. We'll review the probability before entering into the subject. So at the end of this lecture, you will be learning the definition of probability and some basics of probability. So these are the contents we are going to learn in this lecture. So firstly, we'll be defining what is meant by probability and what are the different approaches of defining probability. And we will be seeing the basic definitions like sample space, event, next joint probability, conditional probability. Using these things, we will be defining the Bayes theorem, and also we'll be seeing the independent events, combined experiments, combined sample space, combined events, Bernoulli trials. So before going to the definition, firstly we need to recall what is the probability. So why should I study the probability? For example, if you take a dog bites a man, so it happens in reality. So every day it happens. So there is no information. There is no information in it. So it definitely can happen or may not happen. So if it definitely happens, we can say it is 100%. If definitely don't happen, we can say 0%. But when a man bites a dog, so definitely there is some information. So it won't happen regularly. It happens once in a blue moon. So definitely there is a lot of information in it. Similarly, if you take the sun rises in the east, so it happens regularly. Sun rises in the west, it will not happen. So definitely there is some information in it. So probability gives you the information. The amount of information is described in terms of probability. If it is definite, we can say it is 100%. If it is not definite, we say 0%. So we are unsure about whether it is definite or indefinite. We go for estimation. So that estimation is nothing but the probability. So probability can be defined in many ways. There are different approaches where we can define the probability: classical approach, relative frequency approach, axiomatic approach. Among all these approaches, axiomatic approach is the updated approach and it is the best approach. It is based on the set theory. It will overcome the drawbacks of relative frequency approach and classical approach. So before going to the axiomatic approach, we need to learn some basics like firstly, we need to know the definition of sample space. What is sample space? What is an event? So we must be very much familiar with this terminology before entering into the subject. So sample space. When you perform a random experiment, the total possible number of outcomes are called sample space. For example, when you toss a dice, particularly in an unbiased experiment, so the possible number of outcomes are six. That is the total sample space. Similarly, if you toss a coin, the possible number of outcomes are two, head and tail. So like that, these possible outcomes we call it as sample space. Here terminology must be very clear. Unbiased experiment. Unbiased experiment means it will have equally likely chances. Whereas a biased experiment, you can see in a tossing a dice in a biased experiment, it will not have equally likely chances. Next, the sample space can be classified into two types based on the number of possible outcomes. One is discrete sample space, other one is continuous sample space. For example, discrete sample space consists of only countable number of outcomes. For example, tossing a dice, the possible number of outcomes are six, right? So similarly, in a continuous sample space, take if you are spinning a wheel or a pointer on a numbered wheel of chance, it can it can have any value. If it is ranging from 9 to 10, we say it is a range of values. We cannot exactly predict what is its value. Is it value can be 9.1, 9.12, 9.123, 9.321 like that. So in continuous sample space, generally we will represent weight, height, weight of a person or height of a person, anything, something which falls under the range category, we represent in continuous sample space. We cannot say exact count. Whereas in discrete sample space, we can specify the possible number of outcomes. Everything is countable. Next one is event. So what is meant by event? So any particular outcome of interest in a sample space is called event. So for example, tossing a coin, I can define event something like this: getting a head or getting a tile, or let us take one more example, a random experiment like tossing a dice. The possible number of outcomes are 1, 2, 3, 4, 5, 6. Let us say define an event like getting an odd number or getting an even number. So these are called events. So what is meant by mutually exclusive events? If both the events doesn't have any common outcomes, then we call it as mutually exclusive events. So for mutually exclusive events, in terms of set theory, the A intersection B is null set. If you apply the probability concept for the mutually exclusive event, P of A intersection B is 0. So these are some basics which are required before proceeding to the axiomatic approach. In the axiomatic approach, we define probability with the help of three axioms. One is axiom 1. Axiom 1 tells us, let A be an event defined on the sample space. The probability of an event should be always greater than or equal to 0. It can be 0, it should be greater than or equal to 0. Axiom 2 tells that the probability of sample space is 1. So the probability of definite event, the probability of sample space is 1. Axiom 3 tells us the probability of sum of all the event probabilities is equal to sum of, let us say P of A union B is equal to P of A plus P of B, provided A and B are mutually exclusive events. For example, let us take an experiment. A random experiment is performed. So in any probability calculation, firstly, we need to develop the sample space. Later on, we need to assign the probabilities. We need to define the event, and later on, we need to assign the probabilities. This is the basic and fundamental way in solving the problems. Firstly, we need to define the sample space. Later on, we need to identify the event. And finally, we need to assign the probability to the particular event for the defined event. An experiment consists when two dice are thrown. What are the possible sum of numbers that can happen? Let us say, firstly, we need to develop the sample space. When two dice are thrown, the possible sample space consists of 36 combinations, 36 different combinations. In that, we need to define the event like something like event A defines here the sum of the sum of the numbers on the dice must be equal to 7. Next, event B is defined something like this. The sum of the numbers should lie between 8 and 11. And event C is defined something like this. The sum of the numbers should be greater than 10. So for event sum is equal to 7, the possible combinations are 4, 3 and 3, 4. And 5, 2 and 2, 5. 6, 1, 1, 6. So like this 5, 2, 2, 5, like this different combinations. So according to the classical definition of probability, the favorable outcomes with the total possible number of outcomes gives to the probability. So the total possible number of outcomes are 36, and we need to identify the favorable outcomes of the defined event A. So assign the probability. So P of A is equal to the favorable outcomes by the total possible number of outcomes. So in a similar manner, we need to compute the probability for defined event B and C. We need to identify the favorable outcomes. Favorable outcomes by the total possible number of outcomes is called probability. So there is another way we can define the probability is relative frequency approach. Particularly, this is used in the science and engineering observations, where the same experiment is repeated for number of times. There we use this kind of definition, relative frequency approach. The number of times the experiment is repeated to the total number of times favorable times divided by total number of times the experiment is repeated. So particularly this relative frequency approach helps us in determining the accuracy and the precision of a particular experiment. And the problem with this relative frequency approach is this is suitable for the experiments which is repeated many number of times. This may not be possible in practice every time. So the relative frequency approach fails to define the probability in such conditions. So axiomatic approach is the best approach where we can apply the axiomatic approach for any kind of scientific and experimental observations, any kind of practical applications. Now let us see the definition of joint probability. Joint probability means let us define the events A and B in the sample space S. So the joint probability is mathematically defined as both should happen simultaneously. The simultaneous occurrence of both events A and B is called joint probability. So as per the definition, we know that P of A union B is equal to P of A plus P of B minus P of A intersection B. So here P of A intersection B is nothing but joint probability. The simultaneous occurrence of A and B is called here joint probability. So P of A intersection B can be mathematically formulated as P of A plus P of B minus P of A union B. Next, another definition required one is conditional probability. Conditional probability is defined for two events. So let us define conditional probability here something like this. Event B has already happened and the event B probability is a non-zero probability. Now, what is the probability that the happening of event A provided event B has already happened is given by P of A given B is equal to P of A intersection B by P of B. P of A intersection B is joint probability. P of B is event probability. The condition on event probability is it should be always greater than 0. So note that if both the events A and B are mutually exclusive, we know that already we defined the mutually exclusive events. For mutually exclusive events, the probability is P of A intersection B is 0. So in that case, conditional probability will not come into picture. P of A intersection B is equal to 0. So conditional probability is a defined quantity, hence it cannot be proven. So this is one example where we can compute the conditional probabilities, event probabilities, joint probabilities. Here is a box, here is a table which represents the resistance and its corresponding tolerance values. So we have taken in the first column different types of resistors which are having values 22 ohms, 47 ohms, 100 ohms. In the second column, it represents 5% tolerance resistors. In the third column, it represents 10% tolerance resistors. In the fourth column, it represents the total quantity of the resistors. So totally, we can see that the 22 ohm resistors with 5% and 10% tolerance are 24. And you can see here, these are 22 ohm resistors, total quantity, and 44 ohm resistors, total quantity, and 32 quantity for 100 ohm resistor. Total number of resistors are 100 resistors. Okay, so we need to compute the, before going to the computation of probability, we need the definition of the events. Here, events are already defined in the problem itself. The event A tells us drawing a 47 ohm resistor from a pack of 100 resistors. And event B gives to is defined something like this, drawing a resistance with 5% tolerance, and event C is defined like this, drawing a 100 ohm resistor. So firstly, we see the calculation of the event probabilities. The probability of drawing a 47 ohm resistor. Totally, the 47 ohm resistors are 44, the favorable outcomes. So the total number of resistors are 100 outcomes. Among 100 resistors, we need to choose a resistor which is having 47 ohm resistance. So the possible combination is 44 C1 by 100 C1. So the event probability of A is 44 by 100. Similarly, the event B is defined something like this, drawing a resistance with 5% tolerance. The 5% tolerance resistors are totally 60. So now the event is defined something like this. I need to pick up a resistor which is having 5% tolerance from the 100 resistor. So the probability of event B is 62 C1 by 100 C1. Next, similarly, event C probability, drawing a 100 ohm resistor. Drawing a 100 ohm resistor. So drawing a 100 ohm resistor, the total number of 100 ohm resistors are 32. 32 divided by 100. Next, coming to the joint probabilities. So joint probabilities here, the event A and event B should happen simultaneously. The probability of drawing a 47 ohm resistor with 5% tolerance. We need to identify the combinations. How many combinations are possible with both characteristics? One characteristic is 47 ohm resistor, other characteristic is 5% tolerance. So both characteristics having the total number of count is 28. So 28 resistors are the total. So 28 by 100. So like this, we need to compute the joint probabilities. And last one is P of A intersection A given B is conditional probability. So in the conditional probability, we will be seeing two events. One event has already happened. What is the probability of happening of another event? We need to compute. For example, P of A given B. In this probability, the event B has already happened. What is the probability of picking up event B has already happened? What is the probability of happening of A? So event B means, so I have already picked up the 5% tolerance resistor. What is the probability that among the 47 5% tolerance resistor, what is the probability that it will be a 47 ohm resistor? So totally 5% tolerance resistors are 62. So but the event A is drawing a 47 ohm resistor. So among the 5% tolerance resistor, I need to select a 47 ohm resistor. The possible combination is 28 by 60. So like this, we can compute the conditional probabilities. So with this example, we can see the difference between the event probability, joint probability, as well as the conditional probability. So next, Bayes theorem, very important, which will be helpful in almost in all subjects we'll be using. Today's booming subjects are machine learning, artificial intelligence, data science, deep learning. So in all these subjects, we'll be using the Bayes theorem. So Bayes theorem is very important in estimating the priori probabilities and posterior probabilities. So the probability of event A is defined on the sample space with the help of conditional probabilities. So this is called total probability, which is used in the denominator part of the Bayes theorem. And so in the mathematical definition, we will see this. See here, the probability of an event A defined on the sample space can be expressed as P of A given Bi by into P of Ba. So this is the total probability of event A. So now coming to the Bayes theorem. So Bayes theorem, see here, the event A has already chosen what is the probability that it comes from Bn. So this can be expressed as P of A given Bn into P of Bn divided by P of A, which will be very helpful in solving the problem. For example, see here, a person planned his birthday on an open desert. Unfortunately, the weather forecasting predicted a rainfall on the birthday. Over an year, it is observed that there is rainfall only 5 days in a total year. If rain occurs on the birthday, the forecasting prediction will be 90%. So they calculate the probability of rainfall on that birthday. So anyhow, he is celebrating the birthday. What is the probability that rainfall on his birthday? So here we can apply the Bayes theorem concept and we can solve the problem very easily. So like this, different problems we can solve using Bayes theorem. This is an example which we see in digital communication. So in the digital communication also we'll be using this Bayes theorem for solving the problems. Next one is independent events. Two events are said to be independent if one event is not affected by the occurrence of other event. So when the events are independent, the conditional probability will become an event probability. You can see here P of A given B will be P of A. As per the definition, P of A given B is P of A intersection B by P of B. But P of A intersection B is P of A into P of B. So P of B cancels out. So P of A given B will become P of A. The conditional probability will become event probability. So there are mathematical difference between mutually exclusive events and statistically independent events. For mutually exclusive events, the condition is P of A intersection B is 0. For statistically independent events, is P of A intersection B is P of A into P of B. So At the end of this lecture, student will be able to learn the definition of probability and some basics of probability. Thank you.